This is the recording, the supplemental recording for that would have been presented on Friday the 10th. I'm doing it today on the 13th, a little bit before we move for our regular class in advanced. So let me go over to where we left off in pancreas. I don't think there's a ton left in each of these two chapters that are there. And this is kind of where we left off. We have finished the liver. There wasn't a lot to say about the liver comparatively, but the pancreas is so critical because of all the proteolytic enzymes and other enzymes, not just protein digestive, but the array of enzymes that can compose a vast part of pancreatic juice. So they call them zymogen because they're enzymes in the inactive form to avoid self-digestion, what they call proenzymes. This is exocrine in nature. The endocrine portion of the pancreas lies more externally. This is more internally. The duct they use is called the pancreatic duct for these internal secretions. That's what defines them as exocrine. The endocrine portion sort of oozes out externally and is captured by a rather substantial amount of blood vessels that surround the pancreas, just like any of them. And so, as you're going to see, this duct leads into the duodenum by way of what we call the common bile duct, okay, now called the hepatopancreatic sphincter and hepatopancreatic duct. And they go directly into the duodenum or duodenum, depending how you pronounce it. And as you will see, it consists a lot of water and a lot of bicarbonate for its alkalinity to offset the excessive, tremendous amount of acidity coming from the stomach that's there. And so you can look at all these granules. This would be a typical aspect of a duct. Bicarbonate and water secreted here, sort of in these little ductules. And how you can see the duct. And again, the abundance of characterized by a lot of rough endoplasmic reticulum, a lot of mitochondria. There's always a large anything that produces a lot of proteins, and effectively these are almost all proteins. These enzymes, I don't get a lot out of that. As you see the production a day, we're making the better part of 1.5 liters, pH of 8, neutralizing the acidic chyme coming out, principally bicarbonate. And the enzymes, again, are almost always in this inactive phase. I can't even think of any. I shouldn't even say almost, they are. Many of them are proteases, so they're protein digestion. And as I said, when someone has pancreatitis, these leak out into the abdominal pelvic cavity, and they digest proteins. It doesn't matter what the protein is. That's what all of these enzymes, they digest things they encounter. They don't have to be in a special place for them to be activated that are there. So proteases secreted in the inactive form to prevent self or auto digestion. Remember the last time we saw amylase was in the mouth. So now we're not going to start breaking down carbohydrates. We start in the mouth, maybe just starting to break down carbohydrates. Now we're going to complete the task in the small intestine where this is going to. And the same is for lipids, even though we've addressed that both in the mouth and in the stomach. And first time we're going to address nucleases. Effectively what happens, all of these are leading to the small intestine, and that's where the vast majority of digestion occurs, and certainly the vast majority of absorption. Because when the whole ball game is breaking down all of these agents, all of these nutrients that we have ingested in a form that can be brought into the cell, either directly into the capillary bed or directly into the lacteal, the lymphatic channel that's there in those literally millions upon millions of villi that are effectively the digestive structure in the small, absorptive structure rather in the small intestine. They get activated when they reach duodenum. Again, it's usually pH. Why that can happen in the bowel, except if it gets out, like in pancreatitis, you have areas, effectively the contents are neutral, but there's always going to be little amounts periodically of acidity or alkalinity floating around that will activate these things. So here you can see an enzyme bound to plasma membranes of the duodenal epithelial cells is produced there. And what it does is it begins this series of activation. And so this enteropeptidase is the key player. And the enteropeptidase, what it does is it activates, and this is the thing, trypsinogen to trypsin. And then once trypsin is activated, it acts, and again, it's like a cascading catalyst. We activate the trypsinogen to trypsin, and trypsin can catalyze and then change things chymotrypsinogen to chymotrypsin, procarboxypeptidase to carboxypeptidase. Okay, it can activate more trypsinogen, so it's only self-perpetuating if you want to think of it that way. And you can see here's that membrane down enteropeptidase, and you can see that how it activates. And here the trypsin again can activate these as well as come back and activate itself. So it's a well understood structure. Here's the pancreatic duct itself. Here are these other ductules, and it joins, although it's not pictured here, coming in from by another stem coming in and forming that we used to call the common bile duct, because bile coming from the liver and or the gallbladder. So now we call it the hepatopancreatic ampulla, and there's a hepatopancreatic sphincter. Okay, and it looks like, I'll show you, it looks like a mini volcano and whatever. And even there's a smaller duct from the pancreas that also empties, and it doesn't use that same duct. So you'll see some of these pictures. We saw this before. Nothing special there. And all of it is regulated. I mentioned these two in passing at the end of our last meeting, and that was where we're on-site meeting, which was the action of once the acidic chyme enters, the stretch receptors, the pH receptors, the osmolarity receptors in the start of the small intestine, the start of the small bowel, once they are stimulated, they immediately start to release cholecystokinin and secretin. The cholecystokinin goes to the liver and triggers the release of bile. It's basically sort of saying, look, we've got food coming in from the stomach. There's a good possibility there's fats. Generally, there's an assortment of things, so we need bile. And at the same token, everything else, we need secretin, because to complete the digestion and then the absorptive process, we need secretin because it's going to produce all of those useful enzymes initially in their inactive state that are going to become activated. It's kind of the way this whole thing is triggered. So, and again, I don't really get too much into the enterohepatic circulation, but what happens, it keeps recycling the bile salts 95%. And so secretin, when it's exposed to hydrochloric acid and fatty chyme, stimulates the gallbladder to release bile. Again, the fatty nature of the chyme. And again, once we get active in this process, that sphincter is going to open, bile is stored in the gallbladder and released only with contractions that occur there. And they're just showing you, as we looked at before, this enterohepatic circulation. I don't think it's a big deal. So here, it enters in the first step. It's secreted by the duodenal enteroendocrine cells that are there. These are located in the crypts, CRYPTS. It's a fancy name. They're called crypts of Lieberkühn. You don't have to know that. So here, just like we had in the stomach, these are enteroendocrine cells. They're triggered right away by the nature of the chyme, causing this to be released. Then it stimulates this. The secretin causes secretion of the bicarbonate, the water, all those pancreatic juices, the bile, gallbladder contracts, etc., etc. Understood. And that's really the next phase of this. So once we're done with that, we really have one more, and it's a limited amount in that last PowerPoint slide that's here. And now the small intestine really is more about the anatomy we went over. I'm not going to revisit it. All the different parts of it. You saw that illustration before, the blood supply. Again, all of these modifications take this 3/4 inch to inch diameter hose, maybe 20 feet long. And when you split it and spread it out with all these adaptations, you have the size of a tennis court. And it has to do with the folds, basically shooting through in a spiraling action for maximum contact. These little nubs we call villi, which means fingers, and the fact that they're covered, each of those fingers are covered forward, backward, around, through, all over with simple columnar cells where the absorption can occur, and to increase their surface area, they have microvilli. And so the so-called brush border. So you'll see all of these and you can read through it. This is just a review. In each one of these villi is the lacteal. The lacteal facilitates effectively an end of a lymphatic capillary that allows for the absorption of fatty substances, heavier substances, sometimes bad things that get absorbed through there. And it's surrounded by a tiny capillary network that really will absorb and bring into the circulation everything else. And again, that's going to the hepatic portal circulation so it can be processed in the liver before it gets into the general circulation. And then you're going to see in this brush border has the very famous brush border enzymes, things that will take a disaccharide, which is too large to absorb into a monosaccharide. It'll take a dipeptide and break it down into individual amino acids that can be absorbed, etc. And that's what you'll see throughout the physiology. Here's the look. Gives you an idea of how the brush border all throughout here on either side, going forward, going backward, all around are this layer of cells that create this immense amount of surface area. Here's the individual crypt. In green, you can see these are the enteroendocrine cells producing the secretin, the cholecystokinin. Pan cells, again, producing useful substances, sometimes lubricants. Sometimes these are leading pathways leading into lymphatics. This is a good looking one from a micrograph. You can see the crypt itself, this indentation next to it. And you can see here's the lacteal, and you can see this abundance of, and effectively this is all one layer. It's not pseudostratified. Here you see the goblet cell, etc. Mucus granules all over. These are the microvilli, and it's a really good illustration. And the cell where the digestion and absorption is taking place is called an enterocyte. Again, enteric means alimentary canal cell. It's a generic term. These are the most replicative, fastest mitotic cells in your entire body as an adult. So effectively, every 3 days, roughly, they're all being replaced. So it's continuously billions of cells a day being replaced. And so here are the crypts that are there. The enterocytes make up the bulk of the epithelium. Tight junctions, again, prevent it from going directly in or irritating. Again, there's a lot of chemicals that are in there. There's those proteolytic enzymes. All of that's part of it, where the junctions are so important. You can see the villi are there. Crypts produce yet more intestinal juices, watery mixture of mucus, carrier fluid for the chyme. The goblet cells are there for the mucus, the enteroendocrine cells, Panna cells. These are more defensive. That's why it's hinted at. They secrete immunological elements that are there, defensins and lysozyme. So they're addressing the likelihood that even though by traveling through the stomach and being bombarded by all that acidity and being churned, there's still additional measures for bacteria that somehow get through that onslaught. And now you have more measures to destroy them. And then furthermore, if it's still there, then it goes to the liver. So as you can see, renewed every 2 to 4 days, average about 3 days, continuously. About billions of cells. Lots of lymphoid tissue. This is where we see Peyer's patches. In that lamina propria, the layer underlying it, drink. And the farther you go, as you start to go, not in the duodenum, starting in the jejunum, but certainly in the ileum, where you see lots of these, because now we're getting a larger accumulations of bacteria. IgA is there, plasma cells are there, in case antibodies are needed. Think of all of it. It's well organized for that. And the duodenal glands, alkaline mucus to neutralize the acidic content. So between the bicarbonate and the alkaline mucus, you're achieving not having that acidity destroy things. Again, if it comes out, the chyme comes out too fast, then you get, rather than having a gastric ulcer affecting the stomach, you have what's called a duodenal ulcer. Typically, it doesn't hurt when you eat. That's typically the gastric ulcer, but you give it 20 to 30 minutes and stuff finally starts to go through into, through the pyloric valve into the small intestine. That's where it begins. So the duodenal ulcer is a slightly different, way of presenting itself when you take a history. This is the number one area for chemotherapy and radiation therapy. These are the most rapidly dividing cells. Number one. nausea, vomiting, diarrhea. Standard stuff. You know it's going to come. And what physicians do who are doing these kinds of treatments are well aware of it. And they have to take, you basically, you know what the complication is, and you treat the complication before the treatment is worse than the complication. For a bigger part of the complication is worse than the treatment. A couple of liters a day. Major stimulus is the acidity or the hypertonicity. As you can see, alkaline and slightly it's isotonic with the blood, largely of water and some other stuff that's in there. 3 to 6 hours to do all the absorption. It's a pretty long journey before this stuff gets. I mean, we're talking, depending on how fast it makes its way through. I mean, you're talking 6 to 8 hours, I would say, on average, for you to had dinner last night for that, somewhere in the middle of the night. It's starting to make its way into the colon, gives you an idea how long it's going to take to pass after that. Okay, all of these things are imported from the liver and the pancreas. Respiratory enzymes are bound there, and they're the final digestive step. And so this is how it's regulating. Chyme entry is hypertonic. Chyme delivery is slow. The acidity mixed with the bile and pancreatic juice. And again, there's reflexes and there's local hormones that are related, that are there to control the flow that goes in. And again, segmentation, the way things move around, peristalsis. There's a hormone called botulinum down the late phase. I mean, I'm not worried about botulinum or these migrating motor complexes that are there. So undigested food, bacteria, debris, mostly cellular debris, are moved toward the large intestine. Your feces, again, to restate it, is about a third water, it's about a third undigested food, and it's a third cells. Okay? And as you can see, complete trip from the duodenum to the ileum takes about 2 hours. So that's the first stuff that you're eating. Maybe it takes a couple hours in the stomach and a couple hours in the duodenum, at the very least, before it makes its way into the large intestine. You saw that illustration before. And reflexes control the outflow of the chyme into the large intestine. Okay. I think that basically covers it. Not a lot to say here because there isn't a lot of physiology. It's basically it's non-essential tissue. You could do without it. You could remove technically all of the colon. Okay. Because the absorptive fortune, the limited absorption that occurs there is basically some water, some electrolytes, making some vitamins, and you can compensate for those if somebody has to lose their colon. And typically that happens with somebody. My first girlfriend had ulcerative colitis. After a number of surgeries, they finally said that colon's got to go. Basically, they just pulled what's called a J pouch. They pulled the jejunum down and basically tack it on to the rectal area, and that's how you go. Not easy for the limited conversations I had with her, 20 years ago. I have no idea what it's like now. And again, the appendix, big job again, basically is receding. I mean, if it ruptures, peritonitis, all that nasty bacteria into the abdominopelvic category. But typically why we no longer take away like tonsils or whether it's an appendix, again, it recedes. It helps to recede with good gut bacteria that's so important. Not a whole lot. That's all. And again, thousands of different types of bacteria outnumber the cells. Imagine that 10 to 1. That's just how immense there is of microorganisms that are in there. Ferment that produces gas. There isn't that much gas as people think. Just some people, depending on what they eat, and obviously some people have a tendency to release more gas than others. And a lot of it has to do with food. What do they do in there? Synthesize some B complex and some vitamin K, and you can supplement for those. So it's not, again, that's why it's not keep pathogenic bacteria in check. Because they're good bacteria. And again, a lot of these T cells presenting, triggering the IgA, that is. So again, it's almost like environmental sampling that's done by those antigen presenting cells, those dendritic cells, and keep our immune system in tune. And in this case, they're also keeping your immune system in tune here. A lot of evidence about this. I don't get into it, but you can look through this. Again, we see a lot. Antibiotics are the big problem. C. diff, and if you didn't learn about something called VRE, vancomycin-resistant enterococcus, it's a real problem. And I had this, the C. diff, and awful. Not I'm not. To me, there's nothing else here. One thing I would mention, that's more anatomical. As we get older, again, it's like a bubble in a tire. The smooth muscle lining develops imperfections and weaknesses in it. And because of all the segmentation and peristalsis, you get part of the mucosal linings, not the linings in the submucosa and the mucosa itself, basically protruding out through these weaknesses in the wall. They're called diverticulum. And so they're herniations of the mucosa. We have a lot of them. We call it diverticulosis, mostly in the sigmoid. And when it becomes inflamed, stuff gets trapped in there. It can burst and leak. It's diverticulitis. And again, now you're getting lots and lots of nasty bacteria that would normally be sequestered in the gut to help us, becoming a real mess of all this and getting gram-negative sepsis. Irritable bowel is different. People have that. It's certainly stress related. Sometimes I think it's overdiagnosed, but there's a lot of problems. A lot of people, everybody deals with stress differently. A lot of people, in a stressful situation, they're running it just affects their. Oh my God, it sticks to my stomach. And basically, that's a lot of times that's where stress is translated to. They don't do anything with defecation. So there's not a lot. And again, diarrhea means the food's moving too quickly. Constipation's moving too slowly. Without going crazy about it. And again, digestion breaking it down. And it has to be small enough molecules. You'll see this. It's all about breaking macromolecules into monomers. So you go back to your biochem, and you know all about this stuff. Well, a variety of glands, which would be like intestinal crypts and gastric pits, accessory glands, and pancreas, all of its hydrolysis. Tight junctions, make sure it's okay to do transcytosis and go through the cell. We don't want to go in between the cells. So it either do transcytosis or it could have a certain amount of processing and then be secreted by the cell on the other end into the bloodstream that are there. And so those tight junctions play a really important role. So monosaccharides, again, those amylases are breaking it down into oligosaccharides and disaccharides. These are the three common disaccharides. We only absorb monosaccharides. That's why lactose intolerance typically creates diarrhea, and it can be very severe. There's a lot of people, stepson, for instance, I mean, if he gets any dairy at all, oh my gosh. I mean, it hits him fast. Really, I mean, we're talking fast. I mean, every so often that happens, you should be careful to be dairy free, and you don't look at the ingredients and something in the box says contain. That's why you got to read all the things for people with allergies and sensitivities like that. Is it contain milk or is it some kind of dairy product? You have to be on top of that. It just shows you how it ends. And I'm fond of saying all roads eventually lead to glucose, because even though we absorb these, we'll convert them to glucose. And you can look at this. There's a lot of these. You don't have to know all these names or anything like that. And you get monosaccharides co-transported. Typically, it's secondary active transport with sodium. It's the major way it goes in, and they make their way out. You can see what happens with regard to these things. They can be actively transported out. We have different carriers, secondarily moving them in, and then moving them out. Here's the lactose intolerance nugget. And the lactose basically creates an osmotic gradient. It pulls water, hence that profound diarrhea. And because of the reaction that ensues because of this is really inherently an irritant for whatever reason. And yeah, gas, bloating, cramping, particularly cramping. And I mean, we used to use this for one of my kids. He's not lactose intolerant anymore as an adult. We used to put the drops in. These were the days before we didn't see almond milk and soy milk and oat milk. I mean, if we had it, we keep almond milk at home all the time. We use a lot of it. Anyway, proteins, again, they keep breaking down. It's got to be amino acid monomers. Starts in the stomach. And the pepsin is only active in an acidic environment, so the higher pH, the alkaline environment, limits it. And so eventually it's going to make its way to those brush border enzymes. And that's really the critical piece that's here. The trypsin, chymotrypsin, and carboxypeptidase, the brush border enzymes are additional dipeptidases, aminopeptidases. They break them down into small until the individual amino acids, and the amino acids are co-transported. So again, mostly secondary active transport. The difference with fats is the acid involves emulsification. That's where the bile salts come in. They treat with bile salts. They break down them into smaller ones. And then the lipases do their thing. They break it down into the glyceride and fatty acids. This is more how it's carried in the bloodstream. I don't go into mycelial formation, the bile salts, and the less I'm not worried about. Just understanding it breaks it down. And again, there's different ways they're carried. When you have a lot of these, this is the problem. I mean, they have to go through the lymphatic system. They enter pretty much by that at and around the thoracic duct, back into the general circulation. The trouble is, if you're eating excessively fatty foods, it becomes a problem. It's a lot harder to deal with those as they get into your circulation, unfortunately. So those chylomicrons are things that you can get a lot of, and it's really, those are in those very low density lipoproteins. They're often carried with, and that's not a good thing. They're really predisposed to problems. So, I mean, the more you have these, you have limited amounts of this, okay? And that's where some of the problem is as well. And same thing with nucleotides, into nucleotide monomers, and they break them down into free bases, pentoses, and phosphates. Okay, and they actively transport them as well. And the vitamins in the small intestine, fat soluble absorbed, water solubles are absorbed without going crazy about any of this stuff. Don't forget the intrinsic factor. And again, most of the even though we do electrolytes in the large intestine, again, we don't need the large intestine, so the vast majority of electrolytes, iron, calcium, sodium, chloride, etc., etc., etc. Pretty much the small intestine does everything necessary. That's there, and this is how we transfer iron around, and that can cause some people with limitations here of these proteins. Obviously, vitamin D, parathyroid hormone, important about the calcium. We've already gone over that. The water is reabsorbed in the small intestine, even the large intestine. And these are problems that go wrong. Malabsorption, anything, and malabsorption plays a big role with any of the limitations there. And it can come from infections, it can come from antibiotics, it can come from diets, it can come from hereditary, celiac disease, gluten-related problems, immune reaction to glutens. To avoid gluten, which you have to be on top of that. Once you know you have it, there's so many things today to be advantaged today. With vegetarians, vegans, gluten-free, lactose-free, it's the type that we have. Sometimes it's costly, but we have them available, and that is it. That is the lecture that I owed you. I'm happy to get that done, and I'll be meeting with you later today. So thank you very much.